Good day everyone. In this video, let us apply the law of conservation of mechanical energy to the problem on the inclined surface with a spring at the bottom of the inclined plane. And we will provide the stopping distance of the object once we place the object at the bottom of the plane. Now, before that, consider an object that's traveling in space, and we already aware that the particle has the different positions as it moves along the or within this travel. And remember that to any positions of the particle, it has a corresponding total energy assigned as E, which means that we have the total energy at E1, we have total energy E2, E3, and so on to the nth number of points. Now, those are the total energies at the point. Now, the law of conservation of energy says that the energy 1 is equal to energy 2 equal to energy 3 and to the end point of the position of the particle. This means that the energy is always constant because they are the same. Which means that if we sum up all the energies, the sum should be 0. If we consider a closed system, because the law says the total energy is constant. Now, this law can be applied anywhere. No? Just not only at the surface of the earth, it can be applied anywhere. The total energy in a closed system is equal to 0. Hence, the energy at different point is a constant. Now remember that we cannot create energy. All we can do is to transform it to a useful energy. And there are many forms of energy. Now in this video, let us focus on the mechanical energy. So what are the energy that can be collected within the mechanical energy? We have the kinetic energy, because this energy possessed by its velocity. Meaning, if there is a velocity, then there is a kinetic energy other than 0. But when the particle stops, then the kinetic energy is 0. We have also the gravitational potential energy. This energy is possessed by the vertical separation of the object away from the reference line. The reference line is always the horizontal, and the height should be the vertical, which means that all particles have the potential energy, the gravitational potential energy with respect to that level. Now, if the particle is located at the top of the horizontal of the reference line, then the energy is positive. If the particle is at the bottom of the reference line, then the energy is negative. Which means that all particle located at the reference line, the gravitational potential energy is 0 because there's no height. And remember that the gravitational potential energy is possessed with the vertical separation of the object from the reference line. Now, another possible energy is we have the elastic potential energy. If at that point there is an elastic force at that point, meaning it can be provided by the elastic potential energy. And we have also other work done by other forces, the external forces. For example, we have the friction, because friction is always present when there is contact between surfaces. Those are external forces. Or maybe there is a force applied on that. Now, all that energy can be collected as work done by other forces. Okay? And that will be added only at the initial point of travel. For example, if we consider E1 and E3, then the work done by the other forces should be placed at the initial because it occupies, actually it represents all the travel from that point to the final point. Okay? But in the final point, we need only to combine the kinetic energy, gravitational potential energy, and the elastic energy. That's it, no? So, at any point of travel, these energies can be obtained. The total energy, meaning we can say that the total energy of the particle at any point is the sum of all this energy. Okay, now consider an object, an inclined plane whose spring attached at the lower end of the incline, and this plane is inclined at an angle of theta from the horizontal. Suppose we have the object placed at the free end of the spring, and suppose that the inclined plane and the object whose mass is m has a coefficient of friction mu, kinetic friction mu. And remember, mu is a property of material in contact, meaning different materials might have different value. And remember that the coefficient of friction is the ratio between the friction and its normal force. The normal force is always against and perpendicular. Now, the friction is always less than by the normal. That's by theory, and supported by experiment. Which means that the coefficient of friction should be less than 1. So meaning, less than 1, meaning this is a decimal point. This is less than 1. Okay, now if we apply a force on the object that is being connected by the spring, now you will exerting a varying force on that. Meaning if you compress the spring, then your force must be an increasing magnitude. That's according to Robert Hooke on his Hooke's law. You apply the force, and that force is proportional to the spring displacement or stretch length of the spring. Remember that if the spring is on the force where force is equal to 0, then we call that as the stable position of the spring. But the moment you compress or stretch it with the stretch length or compressed length, then you must apply the greatest amount of force at that point. And that will be, at that level, it should be the greatest force you applied on that spring. And remember that Hooke says that the force is proportional to the displacement. The greater the displacement, x, the greater the force. And the relation is linear. That's why we have the spring constant. So if we calculate the force, it should be the product of the spring constant times the x. So, at that level, since the spring was constant, compressed, then it follows that it develops the so-called elastic potential energy at that point. Now remember, it is a rest energy. The moment you release that object, if you release the support of that object, that configuration that the spring was being compressed, then that particle will move up the plane. And take note that the velocity at that point, final velocity, is 0 because it rests at that point. And maybe it will turn back, no? Turn down. Then remember that we release the particle at the point where we stretch or compress the spring, which means that the initial velocity is also 0 and the final velocity is 0. But it doesn't mean that the particle travels without velocity. The fact that the particle travels up the plane, then it must have the velocity. But it started with 0 and it ended with 0. Now what's the reason of having the velocity? The reason is because of the rest energy done by the elastic material. The elastic potential energy is responsible for the particle to travel up the plane. Now take note, once you release the object, then that is the point where the potential is maximum. Now as the stretch length will reduce. The amount of energy is also reduced until zero, which means that if that particle passes through the point of the stable position of the spring, meaning x is equal to zero, that will be the maximum speed of the particle that can be obtained. Hence, the elastic potential energy is equal to zero at that point. Now, since we have already the velocity, or the particle has experienced the velocity, maximum velocity at that point, where x is equal to zero, then it decreases its velocity until arrive to the stopping point, which is zero. Okay? So, the question now is, how much is the stopping distance of this configuration? Now, we will answer this theoretically, of course, no? Because we will apply the conservation of energy. So, our objective is to find the stopping distance given the following. Given the spring stretch or compressed length or x, given also the spring constant, given the angle, given the coefficient of kinetic friction, and given the mass of the particle. Calculates the length, the stopping distance of the particle. That will be our task for this video. Okay, now to solve this is, take note that we will consider the point, no? Because we need 2 points in order to apply the conservation of energy. You have to decide 2 distinct points. Now, if there are 3 or more, then chop it by piece. 1 to 2, 2 to 3, and so on and so forth. Or you can also apply 1 to other point. Apply the conservation of energy. Energy is constant. The total energy is constant. So we will consider our point 1 as we release the particle initially at rest. Then we release it. And it moves up. And it arrives to the maximum highest point, no, of the incline, which has a length of L. Okay? So therefore, we have the energy, total energy E1, and we have the total energy E2 of the 2 points. Now take note that the law says that these energies must be the same. So E1 should be equal to E2, which means that we will provide the total energy initial and we will provide the total energy final, then equate the two, then find something that you can solve. Take note, our objective is to solve for L. Okay? So therefore, we need to identify what are the energies found in the initial point. Okay? And they are, take note, the law says it should be the kinetic energy initial added by the potential elastic potential energy. In this case, we have the gravitational and we have the elastic. So there are 2 forms of the potential energies. And we have this work done by the other. In our case, since we did not apply any force, external force on that, except the friction that affects the motion. So therefore, we have the work done by the friction. We need to do it. Okay? Then, in the final kinetic energy total, we have K2, the final kinetic energy, and we have the final potential energy. Remember again, there's a possibility that we have the 2 potential. We have the gravitational and we have the elastic. But in that case, because we don't have the spring, then this is most probably the gravitational potential energy. Okay, so we need to know what is K1, K2, gravitational potential energy, initial and final, and also with the elastic. So let's start with kinetic energy initial. And we have the kinetic energy final. Take note that the kinetic energy is the energy of the object in motion. This is a moving, no? Meaning there's no kinetic energy of a particle is at rest. So the formula, remember, is 1/2 mv squared. If you multiply 1/2 of the mass multiplied by the square of velocity, that's kinetic energy. So therefore, at initial point, the kinetic energy initial is 1/2 mv1 squared. And remember that our initial velocity is 0, which means that the kinetic energy initial is equal to 0. Now, for the final kinetic energy, same formula. We have 1/2 mv2 squared for the final velocity. But since the final velocity is 0, then the kinetic energy is also equal to 0. Okay, so therefore, we don't have the kinetic energy from point 1 to point 2. But within, no? Remember that within this point, there must be a kinetic energy because the particle was displaced. But because we consider only 2 points of the travel, the initial and the final, then we have to find the specific, no? Or the instantaneous kinetic energy at that point. So in this case, we have the 0 values for the initial and final kinetic energy. Now let's proceed to the gravitational potential energy. We have the gravitational potential energy initial and we have the gravitational potential energy final, UG1 and UG2. Now remember, in our previous video, we understand that the gravitational potential energy is the product of the mass, the acceleration, and its vertical separation, which is height. And take note that the particle, meaning we can solve for the gravitational potential energy if we establish the reference line. Now, choosing the reference line is you can choose any, provided that you can provide the height in that case. Now, in this case, we will consider the reference line at the bottom of the inclined plane for simplicity. Now, remember that above this line, the energy is 0. Above is positive and below is negative. Now, if the particle is located at the reference line, then it follows that the energy is equal to 0. So, for UG1 or the gravitational potential energy initial, this is equivalent to the product of the mass times the gravity acceleration times h1. But in this case, h1 is 0. Why? Because h1 is located at the reference line. That's why we choose this reference line to be at the bottom so that one height should be 0. Okay, but take note, in the final gravitational potential energy, your location of the final position of the object, it has a height and call this as h2. Now remember, this is always vertical. H is always vertical, meaning our reference line is also always horizontal. So therefore, the angle between them must be 90 degrees. Okay? But take note that h2 is not given, but in this case, remember that this is a right triangle whose angle is theta, whose opposite side is h2 and the hypotenuse is L. So we don't have h2, but we can relate h2 in terms of length. And remember, we are to find the length, which means that we can apply the trigonometric function, the sine function, which is opposite over the hypotenuse, which means that h2 is just equal to what? It's just equal to L sine of theta. So therefore, replace h2 with L sine theta. The gravitational potential energy final becomes mgL sine theta. That's it. So therefore, our gravitational potential energy initial is 0, but our final gravitational energy is mgL sine theta. Okay, proceed to the next potential, the elastic potential energy. Now, look at the initial point. The initial point, it contains a spring. Okay? That's the reason why the particle travels up, because of that. So, obviously, we must have the energy at that point. And that is done by the elastic potential energy of the spring. And take note, in our previous video, we learned that the elastic potential energy is 1/2 kx squared. Meaning, the spring constant, okay, multiplied by 1/2 and multiplied by the square of the compressed length, or maybe it is a stretched length. Then square it. So therefore, we must have the spring constant K. Now, by the way, the spring constant is a property of the spring, meaning different materials of spring, different configuration have different spring constant. Meaning it is a property of the particle, and it would not change if the force applied is within the elasticity limits. Take note that if that applied force is within the elasticity limit, the spring will go back to its original length. But if it's beyond the elastic limit, then it will not return to its position. So therefore, the requirements of using spring is, in order to activate its elasticity, apply only a force within the prescribed force, no? And it depends upon the material. If you have the spring in notebook spring, if you apply much force, then it will not return it back because it is beyond the elasticity limits. Okay? So we need the spring constant. By the way, the spring constant can be gathered. No? If we don't know, then we have a simple experiment with that. That's a separate video. So suppose we are already given the spring constant. Multiply it by 1/2 and the square of the spring displacement, or x, then that's the elastic potential energy initial. Now, for the final elastic potential energy, since we don't have the spring at that point, then obviously our elastic potential energy must be 0 because it doesn't have the spring. Now take note that again, in the spring, at the compressed level, the elastic energy is maximum, but it decreases towards 0 when x is equal to 0. And it provides now the energy of the particle while traveling. Okay, so that's it. Now, remember that we have the coefficient of friction, but we did not apply a force. So we have work done by the other. And this other force is done by friction. So we will calculate the work done by the friction. So we have to recall again our previous videos in work done. So remember that forces and its displacement has the work done. All forces must have the work done. And it is, remember, for a constant force, work done is the product of the force times the displacement times the cosine of the angle between them. The angle between them is between the displacement and the force. The angle is always referred from the displacement. It starts from the displacement towards the force. And I go back to my videos on calculating work done of constant force, so to give you an idea on how to do it. Now in this case, remember friction is opposite to the motion displacement. So therefore, the angle must be 180 degrees. So if you apply the formula of F is cosine theta, the cosine theta, which is cosine of 180 degrees, is a negative answer. So it should be a negative frictional force F times the L. The displacement is L in our case, and we don't do L, remember. So our other forces is negative FL. But take note, what is friction? By formula, friction is the product of the coefficient of kinetic friction multiplied by what? Multiplied by the normal force. Okay? The normal force is the force against and perpendicular to the object in contact. Okay? And take note that the normal force for the inclined plane, it is mg cosine theta. So, go back again to my previous video in calculating the normal force. So, in other words, friction, which is mu n, which is equal to the product of the mu times n, but n is equal to mg cosine of the angle theta. And this is the theta to be used. So, we have this one. It is a negative mu mg L cosine theta. This is work done by friction. And this will be our work done by the other. And there's no other force applied. Hence, we have already friction. The reason why the particle stops at that point is because of that friction. And also the what? The component of the weight, which is parallel to the plane. Also a factor why the particle stops at that point. Okay? It is always the energy that produced of the component of that weight parallel to the inclined plane opposes the energy applied by the spring that generates to the object. That's why the particle must have the stopping distance. Okay, so that's it. No, that's physics according to the law of physics. So therefore, we have now our remember that in the final we don't have the work done the other because it's accumulates already on the first or the initial point. So all we need to do now is to substitute these values to our formula. No? So E1, we have kinetic energy 1, 0, and we have two potential energies. One is 0 for the potential because the reference is located at that point. Then the 1/2 kx squared is the elastic potential. Then minus mu mgl cosine theta by the work done by the other. These are the energy initial or E1. Now this should be equated by E2. Now E2, we have the kinetic energy final 0 and we have the gravitational potential energy mgl sine theta plus the elastic potential which is 0. So there are a lot of zeros. Okay? Eliminate all zeros, then we reduce this to 1/2 kx squared minus mu mgl cosine theta, which is equivalent to mgl sine theta. Okay? That's it, no? So, look at this formula. This result now says that we have the relationship between what? Between the spring constant, the spring displacement x, the mass of the moving object, meaning mass is a factor, and we have the gravitational acceleration, we have the length because the particle is at the surface of the earth, then earth must exert a force on that due to gravity. And it is also a factor of the theta. Now take note, if you increase the angle, then it reduces its length because it is inversely proportional. If you increase also the mass, it reduces the length. Okay, but it is proportional. K, when you look at the formula, L is proportional to K and proportional to X. Okay, so that's it, no? Now, what we can do now is, our task is to solve for L. We need to, how much is the stopping distance? In that case, we will we'll combine all terms that contains L and place it on the right side. Then the 1/2 kx squared should be in the left side. Then apply the law of algebra. Be careful on your algebra. So transpose the term. So we have this one. So we have mgl sine theta plus mu mgl cosine theta is equal to 1/2 kx squared. Okay? Now take note that we want to solve for L. Now all we need to do now is in the left side, we have to combine the common factor. The common factors are mgl. Okay? So take it out. Then we have mgl sine theta plus mu cosine theta, which is equivalent to 1/2 kx squared. Okay, so therefore, this is it, no? Now, this equation now, we can play around this equation. This is for the problem that we have the inclined plane, or we have the plane and place with an object on the spring, then compress the spring, then release. It starts from rest and it ends at rest. So, this is a working mathematical relation on this. Now, since we are trying to solve for L, now all you need to do now is to divide the factors by the sine theta plus mu cosine theta and then mg in order to solve for L. So, divide both sides by this factor and the result is L is equal to kx squared over 2mg quantity sine theta minus mu cosine theta close parenthesis. This is how to compute for L. Meaning, if we have K, X, mass, theta, and mu, then we can solve for this stopping distance. Okay, so to exercise ourselves, let's have this problem. So suppose the problem says that we have an inclined plane, inclined at an angle of 20 degrees, having the coefficient of friction between the object. The 3 kilogram object is placed on the horizontal out at that plane with a coefficient of friction of 0.15. Remember, it is a friction, coefficient of friction is a unitless number. Then the object was placed at the spring in one end of the spring whose spring constant is 4,000 Newton per meter. This is the unit of spring constant. Now, it was compressed. No, applied a force to compress the spring at a distance of 10 centimeters. Now, in this configuration, what is the length that the particle travels up the inclined plane? So, what is L? What is the stopping distance? We call it the stopping distance. So how will you do it? Then all you need to do is to substitute this to the formula. Now K is 4,000. The spring displacement is 10 centimeters converted to meter is divide 1,000. So this is okay. 100, then it should be 0.10. Square it, then divide by 2. Formula, mass is 3 kilograms. So is I 9.81 for the gravitational acceleration. Then the 20 degrees, take the sine of that, plus the 0.15 of the coefficient beneath the friction, multiplied with the cosine of 20, all of them simplified, then calculate, and we have the value as 1.41 meters. Meaning, the particle will stop at a distance of 1.41 meters in that configuration. Meaning, when the spring constant is 4,000 Newton per meter, and if you compress it with 10 centimeters, then the stopping distance is 1.41. Meaning, if you increase the compressed length, then it will stop more than 1.41. If you reduce it with 10 centimeters, let us say 8 or 5, then the 1.41 will reduce stopping distance. Okay, that's the this is according to theory, and you can evaluate this or verify using experiment. But take note that theoretical will provide exact results. And according to the theory, it should be 1.41 meters as the stopping distance. Okay, so that's it, no? So meaning you can play around this formula. Remember, our equation rotates on this equation. Meaning, suppose given L, given the mass, given the angle, given the spring displacement, then calculate the spring constant. In that configuration, it starts from rest and it ends from rest in the spring, and the object was compressed to that spring. This is the working equation. So meaning, solve for K in this case. Substitute the values, then solve for K. Then apply your algebra, then you will be provided with the answer theoretically. Or maybe given the spring constant, given the mass, given the L, given the angle, then you are asked to solve how much distance where the spring be displaced in order to provide that displacement using that coefficient of friction, using that mass. Remember that mass is a function. The greater the mass, the smaller the length. Okay, but the greater the constant again, spring constant, and the greater the spring displacement, the greater the displacement of the stopping distance also. So again, play around on these equations. So when you read the problem, it satisfies this condition. It starts from rest, and will end at rest. Okay, regardless of what angle, no? Meaning, if you increase the angle, what will happen? It affects the displacement, diba? Meaning, if you increase the angle, when you look at the formula, it is proportional. The length is proportional, inversely proportional. No, inversely proportional to the angle. Okay, meaning if you increase, then the displacement is decreasing also. If you increase the angle, the length will decrease, inversely proportional. Okay, so Suppose the angle is 0, what will happen? Try to imagine. If this is 0, then this will become 0. Sine of 0 is 0, and this is cosine of 0 is 1. So, it will reduce. Now, you can also have, for example, if the friction is negligible, then mu is equal to 0, then this term becomes 0. So, we have only this one. Okay? Now, again, let us say that the angle is 0. So, if the angle is 0, then what will happen? This term becomes 0. Okay, suppose we have the friction. Okay, then it follows that the cosine of 0, remember, is 1. So, substitute the value. So, this is 0, term becomes 0. But the cosine of 0 is 1. So, we reduce this, and L is equal to k squared over 2 mu mz. That's it, no? So, we played around the problem. So, you can adjust the angle, viewers. Now, what will happen if mu is 0? What will happen? What do you think? Look at the formula. This formula and the previous formula we derived. If mu is 0, what will happen? This term becomes indefinite, which means that the particle travels in an infinite distance. It won't stop if friction is 0. Okay, that's the theory says. No, and it's true. No? Because there's no stopping force on that. So meaning the particle moves at a constant speed. Okay, so I think that's all for today. Please see you in the next video for some tutorials on physics.